In this lecture, we're going to talk about valence bond theory and hybridization. Now, the reason why we need a different theory other than the Lewis theory is because Lewis theory does not give good numerical prediction. We've seen examples of bond lengths. So say, for example, the distance between two hydrogens in an H2 molecule or two fluorine in an F2 molecule are different. However, according to Lewis theory, these distances will be the same. The other reason is that the SCPR gives good approximations for the bond angles in molecules, but cannot be used to actually get precise measurements of the angles. So the valence bond theory is another theory that is based on the idea that when two atoms will form a bond, will preserve their identity, and use the valence electrons to form the bonds, which seems very similar to what Lewis theory did, but we can see that this is how the bonds form, so it's slightly different. So you have singly occupied atomic orbitals. So each atomic orbital here, these are two s orbitals for the hydrogens, will overlap. Each orbital contains one electron, and the overlap will generate a region that is what we call the bond. The reason why these bonds will form is because the potential energy for the entire system is going to be the lowest when the two single orbitals are at a precise distance, which is the optimal distance. So you can see when two orbitals are far apart, and you can see them on the right of the screen, there is no attraction. Then as the distance gets smaller, they reach this optimal distance, at which they stop, because if they come too close, repulsion because of the nuclei comes into play. So summarizing the idea behind the valence bond theory, we can say that the valence electrons in the molecules that are in the atomic orbitals are the one responsible for the formation of the bond that occurs when the orbitals overlap. The overlap of the orbitals can occur between any of the orbitals that we've seen, the s, p, d, and f. It can also occur with using hybrid orbitals, and we see what these are later on. The geometry of the overlapping orbitals is what determines the shape of the molecule. What does that mean? So imagine the overlap between p orbitals and s orbitals. Now you see the p orbitals sketched here. Now so this is SH2 as a molecule. If the two hydrogen approach, they have their s orbital, these will be able to overlap with the p orbitals of the sulfur. They will do that in a specific direction that is, as you can see, the one determined by the geometry of the p orbitals. So now we're going to look at examples of how a bond is formed with this VB theory. So we have the example that we were looking at that was unexplained by Lewis theory. So we're looking at the formation of H2, F2, and HF. And we know that the bond length and the bond strength for these various bonds is different, which is not explained by Lewis theory. Now you can see that when the two hydrogens approach, so here are the s orbitals, and they're going to overlap. They're going to overlap along any direction in this case because they're spheres, and they're going to reach an ideal distance from each other. And that's the bond length we were seeing before. The bond length is the distance between the nuclei at this point. When two fluorine approach, however, the situation is different. Now you have the orbital diagram for fluorine, and you can see that the singly occupied orbital is a p orbital. And you see that, so the overlap must occur between the two p orbitals. And this creates a larger distance between the two fluorine nuclei because of the shape of the p orbital. So now you can see why the distance there is almost double as that of the two hydrogens. The distance between H and F is somewhere in between, and you can see that in the table. So how does that happen? So you can see here when the hydrogen, the s orbital, approaches the p orbital of the fluorine, can get closer than the p orbital of another fluorine could, but not as close as when you had the two orbitals from the two hydrogens. So this kind of case scenario explains those facts, explains also the different strength of the bonds, because if you have different orbitals, of course, not only the distance, but also the strength of that bond will be different. Now, here is another unexplained case by Lewis structures. So Lewis structure and VSCPR were predicting that the carbon will form 4 bonds with an angle of 109.5 with a tetrahedral geometry, which is correct, but based on the electronic configuration of the carbon, theoretically those 4 bonds should be different because they will be formed by electrons that are in different orbitals. However, we do know from experiments that these 4 bonds are identical, so some other explanation is needed for this. This is where the VB theory comes in with this hybridization concept. So what they say is that you can take atomic orbitals, so an atom can take its atomic orbitals and kind of mix them up to produce different orbitals that are kind of in between in terms of shape and energy of the two original orbitals. So you can say that you can mix the 2s and the 2p orbitals in the carbon and get 4 different orbitals that are the same. So why will carbon do that instead of just forming 2 bonds, for example? Well, the reason is that if you form more bonds, because energy is released by the system when you form bonds, then the system has a lower energy and so it becomes more stable. So it's more convenient to form 4 bonds rather than 2. The how these hybrid orbitals are formed works that way. So you see the electron diagram there for the electron configuration of carbon. Now, the energy difference between the 2s and the 2p orbital is very small. So carbon can move 1 electron from the 2s to the 2p orbital and gets 4 unpaired electrons. These are not yet identical because you would have 3 identical bonds and 1 that will be different. Now, at this point, what can happen is that mixing of the orbitals, so the hybridization. So you get 4 identical orbitals, and we're going to call them sp3. Why do we call them sp3? Because you have originally 1 s orbital and 3 p orbitals. So you can see in the original when we had a 2s and then the 3 2p orbitals. So when you mix them, you have 1s and 3p. So those superscript, that 1 is always hidden, remember that, those superscript indicate how many orbitals originally you had of that type. Now you have 4 identical electrons, and these can form 4 identical bonds, which matches what was observed experimentally. So these are the characteristics of a molecule that has sp3 hybridization, and you can see that many of the things coincide with the observation that we did for the VSCPR theory. So what changes is the modality in which these molecular shapes are obtained. So you still have a tetrahedral geometry, you still have 109.5 degree angles, and the difference here is that the molecular shape is determined by the directionality of the molecular orbitals. And the hybridization, so this is the one thing we're adding, is a sp3. So we can tell this molecule has an sp3 hybridization because it used one s and three p orbitals to form the bonds. Let's look at some examples on how to determine the number and type of hybrid orbitals that we need for a given molecule. So say, for example, we'll look at CH4. Now, the first thing we're going to do is draw the Lewis structure. And for CH4, it is displayed here. Now, the next step will be to determine the number of electron domains around the central atom. Notice that when we talk about the hybridization of the molecule, we're talking about the hybridization around the central atom only. So in this case, we have 4 electron domains, which means we require 4 hybrid orbitals. Now, in order to obtain 4 hybrid orbitals, we need to look at the ground state configuration, so the electron configuration for the central atom, which is the carbon. We will promote one of the electrons, and then we would create our hybrid orbitals, in which case it comes out to 4. And because we mix together 3 2p orbitals and one 2s orbital, our hybridization will be an sp3. So the hybridization around carbon in CH4 is sp3. Now, the hybridization can be made with different type of orbitals. So we could mix different numbers of orbitals. Like if we mix one s and one p, we have an sp hybridization. We could mix d orbitals. So you can see you have sp3d hybridization. Also, atoms like carbon can have different type of hybridization depending on how many bonds they're going to form. The other thing that is important to remember is that the hybrid orbitals actually have a different shape than the standard orbitals. So you can see on the bottom the standard p orbitals and the hybrid orbital for a p orbital. The hybrid orbital have a shape that allow for a greater overlap. So there are more advantages from an energy point of view and from a bonding point of view. Now let's look at another example. So suppose we have BF3. So we want to determine the number type of hybrid orbitals that we need for this molecule. So the first thing will be to draw the Lewis structure, and then count the number of electron domains around the boron, which is 3. Just a quick reminder, the boron is an exception, so no, you don't form a double bond with the boron and the fluorine. Boron can have an incomplete octet. So back to our hybrid orbitals, we require 3. And at this point, we can do what we did before and do our electron diagram, and then do the promotion and then the mixing. And in this case, you see that all we mixed is one s orbital with 2 p orbitals. So we didn't mix all 3. So we have an sp2 hybridization. So 3 orbitals total. Now, the question is, do we always have to go through the electron diagram to determine the hybridization? Actually not. To determine the hybridization of a molecule, first you need to draw the Lewis structure, then you count the number of electron domains, and then you can choose a type of hybrid orbital that have the same number as the electron domains that you determined. So say, for example, if you look at our cases, so if you have CO2, okay, you have CO2, it will have 2 electron domains around it, which means you need 2 hybrid orbitals. So you can use an S and a P. Why is that 2? S1, P1, remember that. So if there's no number up there, it's like there is a 1, and then I sum up those superscripts there. So that gives me 2 orbitals. if I have, and that's the case of the BF3, we saw 3 electron domains, then we need 3 hybrid orbitals, so we need 1 s and 2 p's. That's 2 plus 1, that's 3. Okay, so every time you're dealing with a molecule, you can simply count the number of electron domains that are necessary, and you can, at that point, just determine the type of hybrid orbital that you need for that molecule. And we're going to look at some example very shortly. Now, what if I have multiple bonds, or if I have more than one central atom? Now, in this case, okay, you can look at the molecule of ethylene. Now you have the carbon to the left and the carbon to the right. These are two central atoms. When we describe hybridization, we can just do one central atom at the time, sort of like the same thing we did with the geometry. So carbon to the left, 3 electron domains, so 3 orbitals needed, so sp2. Carbon to the right, in this case, is the same thing, so 3 electron domains, so sp2 hybridization. Do remember that double bonds count for 1 electron domain, not 2. Now, let's pass on to some practice that we can look at. So here are some examples. So identify the number of electron groups around the molecule with sp hybridization. How do we deal with that? Now we have an sp hybridization. We need to remember that we have one s orbital and one p orbital. So 1 plus 1, that will be 2, right? So 2 orbitals, 2 electron domains. So that will give us an answer as B, okay? Let's look at a more complex question. So say, for example, the question is, give the electron geometry and the molecular geometry and the hybridization for water. Now, how do I approach this? I'm going to pass on to my writing pad, and I'm going to do this. So I have H2O. So the first thing I need to do is do the Lewis structure of this, of the water molecule. And when I do the Lewis structure of this, I know that I'm going to obtain O, H, H, and I have 2 lone pairs. So now what I need to do, I need to count the electron domains. Okay, so this is used for answering all 3 questions. So I have 1, 2, 3, 4 electron domains. So if I have 4 electron domains, now I know that my electron domain geometry is going to be tetrahedral. For the molecular geometry, because the lone pairs don't participate to the molecular geometry, so I'm looking at the molecule without the 2 lone pairs. So I'm looking at my little model here. This is the geometry for the electron domains, but when I look at the water itself, then I need to kind of remove these 2 guys, and so I'm looking at this shape, and this shape is bent. So molecular geometry is bent. What is the hybridization? I need to count the number of electron domains, which is 4, which means I need 4 orbitals. I can have 1 s, and then I can have 3p, so it will be sp3. So my answer will be tetrahedral for the electron domain geometry, bent for the molecular geometry, and sp3 for the hybridization, which is A. Now, the last thing we're going to talk about is the type of bonds. So we talked about the fact that you can have overlaps of orbitals that are along the internuclear axis. These are called sigma bonds. So these are your single bonds. You can also have overlaps of orbitals that are perpendicular to each other. So say, for example, we look at the ethylene molecule. We have our sigma bonds that corresponds to the overlaps along the internuclear axis. And then you can still overlap those p orbitals. So you see those blue orbitals that are perpendicular? Well, those can be also overlapped. When they overlap, now imagine as if you're trying to bend them toward each other, so they kind of grow in size, if you want, in order to overlap. And this bond is called the pi bond, and it's formed by orbitals that are perpendicular to the internuclear axis. And they're also sometimes called banana bonds because of the shape they have. You can see that to the right. The main difference between the sigma and the pi bonds is that the sigma bonds can allow free rotation around that axis. The pi bond don't. So they kind of block the structure in place. So you can have what are called isomers that result from it. So these are geometrical isomers. So molecules that are not quite the same because really you cannot rotate them. Another thing that you can do is you can form pi bonds with more than one p orbital. And what you can do, you can overlap two of those. So say if you have acetylene, how does the triple bond come to be? So you have the sigma bond. So the first bond, the single bond, is formed between the two carbon. And then you see how you have two of those blue orbitals that are perpendicular. At that point, you can overlap them both. And then you have two pi bonds. So at this point, a triple bond is one sigma bond and two pi bonds. So that is all for today.